Hello guys. This is the second part of fluid, which is fluid dynamics, and also this is the last part of fluid. So on this lecture, I will be talking about the ideal fluid first, the properties of ideal fluid, and then equation of continuity, and most importantly, equation called Bernoulli's equation and its application. So first of all, whatever formulas we will derive here in fluid dynamics are based on a very important properties of fluid. It's called ideal fluid. So what is an ideal fluid? So ideal fluid must have four different properties. So these are the properties. So first of all, steady flow. So steady flow means the velocity vector of any moving fluid at any given point in its path should not change. So that means the steady flow. So the velocity should not change. So that is also called laminar flow. Second property is incompressible. That means you cannot change the shape and size of the fluid by applying external force. That means the density is uniform. Density is constant. You cannot change the density of the given fluid by applying external force. Non-viscous means no friction. We do not consider any frictional or drag force. And irrotational means the particle does not rotate. So these are the based on this four fluid properties of ideal fluid, then we can derive the fluid dynamics formulas. So first of all, streamlines. So streamlines are just the path of the fluid molecules that it takes, during the flow. So and you can make the path of the streamlines, make it visible just by adding some smoke particles if the fluid is gas, and you can add some colored dye if the fluid is liquid, yeah, and you can clearly see. And these are the streamlines, and this is the fluid element. And if you want to find the velocity at any given point along this streamline, you just draw the tangent line, and this is the velocity of the given fluid molecule. And this is here in this right picture, engineers use the smoke particles, to test the drag test, to do the drag test in automobile, and you can clearly see this. The streamlines are clearly visible. And here, this smoke rises as laminar flow, streamline flow, smooth flow, and it becomes turbulent, which is little complicated, which we will not discuss. The turbulent flow is little complicated. So the first equation we will be dealing with is in fluid dynamics is equation of continuity, and this is basically the relationship between area of cross section and the velocity in a given pipe, So for example, here let's consider a pipe, of different cross sectional areas like this, and the main idea is the volume flow per second must be same along any point in this pipe, right? And it has to be equal because volume flow per second through from this end, right, where it enters, must be equal to the volume flow per second leaving the junction, because since the fluid has nowhere to go here, whatever volume per second enter here must be leaving here. So for example, at the given time t, say this is the volume element, and after t plus delta t, after delta t times, this fluid would have actually traveled by this distance, but if you see the volume of the fluid per second must be same, must be equal to this, because it has different area of cross section, right? So that makes the delta x greater compared to this. So that's the main idea. So volume flow per second along the path streamline must be equal, and then it leads to a very important equation. So the volume flow per second at this point and that point must be equal. So delta v over delta t, it must be equal to delta v2 over delta t. But delta v is the volume of this cross section, volume of this fluid cross section, right? and volume is area times the height, area times the length. And A1 delta X1 over delta T is same, and A2 times delta X2 divided by delta T. And since delta X over delta T is the average velocity, so that leads to our equation A1 V1 is equal to A2 V2. And this equation is called equation of continuity. And this is basically the relationship between the speed, the velocity, and the area of cross section. So you can clearly see the area of cross section and the speed are inversely proportional, right? You can clearly see from this equation. And this is called the area of continuity. You know, this is the first equation in fluid dynamics. So, how do you define the volume flow rate? You know, flow rate of volume flow rate through any given pipe. So, volume flow rate is simply the this A1 V1, the product of area of cross section times the speed, the velocity. So, A1 V1 must be equal to A2 V2. That's also called the volume flow rate. And its unit is standard unit is cubic meter per second, or liters per second, or gallons per second. These are the subunits. And in general, you can clearly see, in general, you can say the volume flow rate of any fluid through the given pipe is area times area of cross section times the volume. Times the velocity. And here's some example. Since area of cross section and speed are inversely proportional, so in this bathroom faucet, you can clearly see this water, as it falls, it necks down, right, to a smaller diameter. And it's because due to gravity, the water picks some velocity, and as the speed increases, the area of cross section should decrease from the equation of continuity. And same thing with this, the nozzle. If you put a nozzle, you're reducing the area of cross section, that will increase the velocity of the molecule, water fluid. So here's some example problems that I will separately show you. So back to our main discussion of this topic, which is fluid dynamics. As we know from the continuity equation we just discussed, as water flows from pipe of bigger diameter to the narrow diameter, it speeds up, right? Because this area of cross section is greater compared to this, so the fluid molecules has to speed up. So, but what causes the fluid molecules to speed up? There must be some force, and the answer is the pressure force, right? So, because the fluid pressure inside here must be greater than fluid pressure in the narrow tube. And that pressure, the pressure force, the difference between this end and that end is responsible for speeding up, So, and here's the free body diagram. If you want to draw the free body diagrams, let's consider, any cross section of the fluid molecule, and then if you draw so this side, the pressure force acting on this side must be greater than pressure force acting from the other side, because fluid is moving from left to right side on this, right? So this, and back to our main equation, is called Bernoulli equation, and this Bernoulli equation gives us the relationship between the velocity, the pressure, and the heights. So it's the relationship between velocity and pressure. So how it basically shows how the fluid pressure changes with velocity and height. So it's a very important equation. Bernoulli equation is a very important equation in fluid dynamics, because all the fluid dynamics, depends on the Bernoulli equation. And I'm not going to show you all the derivation, but the Bernoulli equation is based on two main things. So while fluid flows from one end to other end, the main idea is the work done by the fluid, work done during this process will be converted to the change in kinetic energy. It's the work energy theorem that you guys have done in CP1. So the basic idea is work done during this process when fluid flows from one point to other point, you know, having different cross section and different heights, you know, different velocities. Work done during this process will be converted to change in kinetic energy, right? That's the main idea. And change in kinetic energy, as you know, 1/2 mv square minus 1/2 mv1 square, and changes into in terms of density and volume. But work done has two parts. Okay, work done during this process has work done by gravity because it has a change in height, and work done by the pressure difference. Remember, because the pressure here and pressure here are different, right? So that's the basic idea. And then you just said the work done by this process is equal to change in kinetic energy and do some mathematics. And then finally you will end up with this equation, this important equation. So this is called Bernoulli equation. And it simply says the sum of the pressure and the kinetic energy per unit volume and the potential energy per unit volume is constant. See, if you check this equation, it will just continue. P1 plus 1/2 rho V1 square plus rho g y1 is equal to P2 plus 1/2 rho V2 square plus rho g y2 and so on. It will just continue. And this is the statement of Bernoulli's equation. So, but remember, this Bernoulli's equation was derived from work energy theorem. So this Bernoulli's equation is nothing new. It's just the consequences of energy conservation. Okay, it's just the energy conservation. So let's talk about some physical significance of this important equation, Bernoulli's equation. So this is the Bernoulli's equation, main Bernoulli's equation, right? P is the pressure, rho is the density of the given fluid, v is this little v is the velocity, again rho is the density, gravity, and y1 and y2 are the heights, okay, and p1 and p2 are the pressure. And so, for example, we're going to see one special case for horizontal tubes. Let's say the pipe is horizontal flow, and let's see the physical significance. Let's say fluid flows through a tube of different cross section, but a horizontal tube like this, right? And pressure here is so velocity here is v1, velocity here is v2, right? It must be at higher speed here. Pressure here is p1. Let's say you put a pressure gauge, you can put a pressure gauge, right, to measure the pressure, and you also attach a second pressure gauge here to measure the pressure. Let's say this is p1, let's say this is measuring p2, and its area of cross section is a1, its area of cross section is a2, right? And y1 and y2 are same, right? So because it's horizontal tube. So since y1 and y2 are equal, so in this equation you can cancel this term, this third term. So then you will end up with p1 plus 1/2 rho v1 square is p2 plus 1/2 rho v2 square. Let's see what does it say. So for example, so if speed increases, let's say if v2 increases, right, because it has a different smaller cross section, the velocity v2 has to be greater than v1. If speed increases, if the fluid molecule flows faster, then since this is moving at faster rate, since the sum of the pressure and this quantity 1/2 rho v square has to be constant, this sum of this quantity has to be constant, right? So this will automatically decrease the pressure, fluid pressure, and vice versa. And if the velocity, so in general you can say if velocity increases, pressure will decrease, the fluid pressure will decrease, and if the velocity decreases, it will automatically increase the pressure, and they goes inversely. Okay, so our conclusion is moving fluid has less pressure, right? That's what it says. That's the main physical significance of Bernoulli equation, right? So you can clearly see, you can say moving fluid exerts less pressure, has less pressure inside it. So that's our main conclusion. Okay, so that's the main conclusion of Bernoulli equation. So let's see one more example of Bernoulli equation. So we can derive the static fluid pressure, static fluid pressure that we've been doing in the first part from Bernoulli equation. Okay, let's see. So let's say this is region number 1, and let's say this is region number 2, and let's say the valve is closed. So you have a static fluid pressure. So how do you find the pressure here, right here? Okay, so pressure here is, let's say, P2. Pressure here is say P1, and which just happened to be the atmospheric pressure because this tank is open to the atmosphere. And these have the different velocities. So velocity is 0 right now. So let's write down the Bernoulli equation again for two different regions. This is region number 1, which is just atmospheric pressure. This is region number 2, and the valve is closed. So we want to find the static fluid pressure. So P1 plus 1/2 rho V1 square plus rho Gy1 is equal to P2 plus 1/2 rho V2 square plus rho Gy2. So this is a static case, so there's no, the velocities are 0 because fluid is not flowing. So we want to find P2. So P2 is equal to P1 plus rho Gy1 minus rho Gy2. Right. So you can see here, right, from this level. So we are measuring all the heights from this level. So let's make this as reference level. So your Y2 is 0. So Y1 is your H, which is the height. So then P1 plus, so Y1 is rho GH, and this is 0, right? Because this is the reference point. And you can clearly see we end up with the static fluid pressure formula, P1 plus rho GH, right? It's the same formula. So we can derive the same static fluid pressure formula from the Bernoulli equation again. It's basically the same thing. So you can clearly see pressure at the bottom. It simply says pressure at the bottom is pressure on the top, which is simply the atmospheric pressure in this case because it's open to the atmosphere, plus this second term rho G times the depth, right? Depth measured from here. This, in this case, actually this is the depth. This is the total depth, right? And we came up with the same formula that we used in static fluid. So I'm going to show you some examples, for the Bernoulli equation demo. So the first example is this video. Let's first watch this video and then we'll talk about that. So this video is self-explanatory.
In this demonstration, I have two bowling balls hanging from this frame by some strong wire. And I also have a leaf blower, which I will use to direct a high velocity airstream between the bowling balls. The question is, what will the bowling balls do? Will they be pushed apart? Will they come together? Or, because they're so heavy, they won't move at all?
So you can choose one of those. Let's say move together.
So, the two bowling balls came together. They did this because as the air moved between the bowling balls is moving at a very high rate of speed. This lowered the pressure between the two bowling balls compared to the pressure on the outside of the balls. Therefore, they were pushed together.
So here's some other examples of the Bernoulli's effect in everyday life. So for example, the first one is in your house, if you have a say water tank in your house, and let's say you close all the valves, let's say for example, and you notice the pressure in the basement. Make sure you close all the valves in the bathroom and everywhere, and check the pressure. And next you open almost all valve in the bathroom and everywhere, so that you have a nice water flow, and also check the water pressure in this pressure gauge, and you will notice that the water will the pressure in this case, when water flows, reaches always lower pressure compared to when it's in static condition, and this also proves that flowing water has less pressure inside it. And there's many examples. So for example, so why does your car lurch, or vibrate, towards an oncoming truck as it passes you? And it has to do with the pressure difference created by the fluid molecules, motion. So, for example, here, this is this blue is your car. You're trying to make a left turn, say, and a big truck is coming at high speed, say, and as the truck just passes by you, your car, you might have noticed your car just lurches towards the truck, and it's because the high speed truck makes the air molecules to flow with the almost same speed, and that creates a partial vacuum, that creates a low pressure region right here. And because of the higher one atmospheric pressure here, your car simply lurches towards the incoming car. So other example is the carving of a spinning ball. It's basically because of the Bernoulli's effect. It's also called Magnus effect. So a spinning ball actually will not follow a standard projectile trajectory. It will make a curve. So as shown in this soccer ball, kicking a soccer ball. Some professionals can do that because you have to spin the ball. And what's the physics behind that? Let's say here, the ball is moving, say, in this direction, right? So since the ball is spinning, then then since the air molecules are flowing in this way, right down, and the velocity of the molecules in this region will be higher compared to the flow rate, the speed of the molecules compared here, because it's spinning in opposite direction. So that makes the air pressure here slightly less than pressure on the other side, and that makes the curving of the ball. That's the main physics behind that, and it has to do with the Bernoulli's equation. It's the difference in pressure because of difference in velocity, because of the spinning of the ball, that creates a slight pressure difference, and that is enough to bend the ball. That's the physics behind that. And there are many other examples. So how airplanes fly, and how does an airplane get a huge lift, and it has to do with the pressure difference. So for example, this is the airplane wing, right? As airplane flies with some speed, due to the curvature of this, airfoil design curvature of the, this wing, the air molecules has to flow at higher speed because of this curvature on the top compared to the bottom of the wing, and that creates a pressure difference between top and bottom, because since the air molecules are traveling at faster rate on the top of the wing, it creates a low pressure region here compared to the higher pressure at the bottom, and that creates a lift. And here's the same example. So here is the animation. You can clearly see, right, the air molecules are moving faster on the top of the wing, and that creates a low pressure region compared to the high pressure region at the bottom, and that creates the lift. And that's how the airplanes can fly. Same thing with the frisbee, and you can try on your own, actually get a piece of paper and try to blow and you will see the paper gets lifted up. And same thing applies with the frisbee because of the frisbee has some aerodynamic design, airfoil design, and it's same thing as the airplane wing. And there are many examples. So here's called one very good example demo for Bernoulli equation is called Venturi measure. And Venturi measure is simply this actually two vertical tubes. It's filled with some liquid, and it's connected by some tube, uh, but of different cross sections. You can clearly see the area of cross section connected to the middle is much less than the area of cross section to the side. And when so at normal pressure, when the if there's no, and you can blow some air, high speed air through this horizontal tube and that's connected to the top. So when there's no airflow, they must maintain the same height, and it's because of the static pressure, right? Because each of these are at same atmospheric pressure, so they must maintain same height. But what happens if you blow high-speed air using a same pump, right? You connect it to the pump, and then you blow high-speed air, and then you can clearly see, right? This rises up. The fluid on the middle tube has now a higher height compared to what's the physics behind that is because since the horizontal tube connected to the top of this middle tube has lower cross section, that means the air molecules are flowing at higher speed here. That creates a lower pressure region on the middle tube actually here compared to the higher pressure here, and the higher pressure here and higher pressure here. So this is the pressure difference it generates because of the flow, and that is enough to lift the liquid column in the middle tube. And many examples. So how the hurricane destroys the roof, and is basically because it creates a pressure difference region here because your inside the house is at 1 atmosphere pressure, but because of high airflow, wind, it creates a low pressure region, and it just your this gets lifted up. The roof gets lifted up because of the pressure difference.